Right, so another interesting experiment with regards to calcium waves is we've seen how when you have zero calcium in the extracellular fluid, how that causes the calcium waves that are induced by this stimulation with methacholine to gradually lose their amplitude and to gradually tail off into nothing, basically. But there is a way of blocking this calcium extrusion, basically. Specifically, a way of blocking this PMCA. And the PMCA is more physiologically relevant for extruding these calcium ions in this situation, because the NCX really only becomes active when calcium level becomes toxically high in the cytoplasm. So really, in these calcium waves, what's going to happen is the PMCA is the main one that is extruding calcium and is causing a gradual loss of calcium from the endoplasmic reticulum, and is therefore causing the tailing off of these calcium waves. So basically, if we use an agent to block the PMCA, then there won't be any extrusion of calcium from these cells, because the NCX isn't really going to be active, because these calcium concentrations aren't really toxic. So the calcium will remain in the cell, and all of it will then therefore have to be pumped back into the endoplasmic reticulum by Circa. So even though the concentration of calcium in the extracellular fluid is zero, we should see our calcium waves happening just fine, basically. Okay, so let's do that experiment. And basically, the drug, if you want to call it that, pharmacological agent is probably the best way to describe it, that blocks PMCA is actually an ion, and it's the gadolinium ion. Okay, so gadolinium. Gadolinium is an element. It's not gadolinium. Gadolinium is an element. It's in the periodic table. Its atomic number, so let's just have a little bit of a sidetrack where we talk about gadolinium, because it's an element that you've probably never ever encountered before. Gadolinium. It's in one of those sections of the periodic table that you will never have studied, basically, unless you've done chemistry at a degree level. So if I draw a little diagram of the periodic table, it looks something like this. Okay, so then you have 5, I think, columns over there. Right, so, and then you have the noble gases here, maybe. Okay, right. Okay, so you also, there I've missed out the bit that gadolinium is actually in. Right, down here. So, you have the alkali metals here, basically, in group 1. So this is the alkali metals. Then you have the alkali earth metals in group 2, where calcium and magnesium are. You have the transition metals in this middle bit. You have other important stuff over here, like the halogens and carbon and oxygen are near in these groups 4 and group 6, etc. And then you have the noble gases over here. Now down here is a section that you probably have only ever looked at in physics class to find uranium. But this is the section known as rare earth metals. And basically, gadolinium is in this bit of the periodic table, this rare earth metals bit. And it has an atomic number of 64, which means that it has 64 protons in its nucleus. And it's often abbreviated to GD. So if you want to find it on the periodic table, it will be denoted GD. And what else can I say about it? Oh, it usually goes around as an ion. So it goes usually around as a 2+ ion. So it usually has a divalent positive charge. So it's usually a divalent cation. So basically, this gadolinium ion is extremely good at blocking the activity of the plasma membrane calcium ATPase. So it's very good at blocking the activity of the plasma membrane associated calcium ATPase. Which is the protein that is pumping this calcium out and is causing the reduction in calcium in the endoplasmic reticulum, and is responsible for this tailing off of the calcium waves that we're seeing here. So, if we block the plasma membrane-associated calcium ATPase with gadolinium ions, we would expect to no longer see the tailing off of these calcium waves, but instead to see this pattern again. And indeed, that is what you see. When you stimulate with methacholine, with an extracellular fluid that contains no calcium, but does contain these gadolinium ions, then you see an absolutely normal calcium wave that does not tail off. So there's a nice, interesting experiment.